Welcome to Review 2B, which is just a review of the salient parts of Reading Assignment 5. So this is the last review lecture and the last slide for this course. I've just summarized the contents of the slides to follow here, so we will just move forward. Again, I'm only summarizing key points, conventions, procedures, and again I'm going to basically only highlight certain things since we've discussed this material in greater depth in the previous lectures. All right, so one of the things we realize first of all that any vector field can be decomposed into two types of field, a source-free field and a rotational field. And also we found that under specific conditions where symmetry applies, and it would be very simple to apply the divergence theorem in the case of a rotational problem and Stokes' theorem in the case of a source-free problem to solve for the vector field. Also, we can use the principle of superposition if we have multiple objects where each of the objects exhibit a form of symmetry. So just briefly, Helmholtz equation essentially said that we can represent a vector field in terms of the gradient of a scalar potential, and this was actually the flux component of the vector field, and the curl of a vector potential, and this was the circulation component of the field. And these are unique for a given physical vector field under specific conditions, and you refer to the note here that the solution to F is unique if the rho, which is scalar density, and J is a vector, decay sufficiently fast as you approach infinity. And this is the case in practice. All physical problems generally will obey this condition. All right, so we basically were able to take this equation, take its curl, and if you take its curl, you get this result, and also making use of one of the vector identities before, that the curl of a gradient is 0, meant that the curl of the field could be simplified down to just the curl of a vector potential A, and we call this whole vector here J. If we take the divergence of the vector field, then we end up with minus divergence of the gradient phi plus the divergence of the curl of A, but from one of the vector identities in the previous lecture, we can say that the divergence of the curl of a vector field is always equal to 0, and therefore this simplifies down to a scalar function which we called rho. And typically what will happen is rho is given and J is given, and in principle you can solve for the vector field F. But we were dealing with two different types of problems where symmetry can be applied. One of them basically is in a rotational field, in which case the curl of the field will be equal to 0, and the divergence of F is a given. Or you can have a source-free field, in which case the divergence of the field equals 0, and the curl of the vector field is equal to J. So in this case, we can apply the divergence theorem to link rho to F. In this case, we can use Stokes' theorem to relate J to F. And the types of symmetries where it was possible to apply the divergence theorem and Stokes' theorem in the respective problems was when we had planar symmetry, cylindrical or spherical symmetry, when we were dealing with any rotational field. In that case, as I said, you use the divergence theorem to solve for F. In the other case, which is a source-free problem, if J has planar symmetry, solenoidal symmetry, which is basically a circumferential current flow, cylindrical symmetry, which means an axial current flow, or toroidal symmetry, then we can use Stokes' theorem to solve for F. And the principal superposition in a nutshell is shown below. If we have a symmetry problem where we know we can solve for F1 given a J1, and we have a second problem involving a current flux density, J2, and again because of symmetry we can solve for F2. Then if we take the sum of the two vector fields, that is F equals F1 plus F2, and then basically take the divergence of the total, and then basically because of linearity, we can say that the divergence of F is equal to the divergence of F1 plus the divergence of F2, and so the sum of these two would be equal to rho. And so this rho, which is for the total problem, could be broken up into its constituent parts, representing two different problems, or as we call them, subproblems. In this case, basically here, curl, you'd have a J1 for this one and a J2 for this one. If you basically take the curl of the total vector field, again because of linearity, this can be curl of F1 plus curl of F2, which is J1 plus J2. So given a J, You can break it out into two independent j's, each having a specific symmetry. Solve for each one of them, sum the results, and get j. Okay, so effectively, these are the problems that we were dealing with. Now, typically what will happen is you either have a problem where rho is non-zero or j is non-zero. Those are the only cases where we really can consider where symmetry applies. And so that's why we're dealing with these sub-problems up here. All right, what are the classes and problems in the procedure for superposition? So problem consisting of multiple objects is converted into a number of sub-problems reflecting the number of distinct objects. So for instance, if you had a sphere and a cylinder, then basically a sphere would be one problem and cylinder would be a second problem. Each subproblem exhibits a specific type of symmetry, and calculations for each subproblem are performed in translated coordinates. In other words, you are not guaranteed that the cylinder happens to be lined up with the axis of symmetry. So what you do is you presume that it's lined up with symmetry, axis symmetry, and then afterwards you move it back to its original location. Once you basically have done that, then you sum the results, basically get the total vector field. So that's more or less what's basically indicated here. So we have basically point of symmetry if we're dealing with a sphere, plane of symmetry if we're dealing with a slab, and we have axis symmetry if we're dealing with anything which has a cylindrical symmetry. So the two classes of problems are as follows. Objects that appear to have no apparent symmetry can be separated into two or more objects where symmetry applies to each individual object. And then the final result is the superposition of the vector fields for each object. So that's one possibility. The other possibility is objects with different geometries, each having a given symmetry, can be treated as individual problems and solved. In other words, they're distinct problem geometries from each other. And so it's clear just by visual inspection that you have, say, a sphere and a cylinder. Again, the final result is the superposition of the field vectors for each object. So what is the superposition procedure in a nutshell? Well, the sequence of steps to compute the total field at a particular point is as follows. The first step is to determine the field for each source in an appropriate coordinate system. The second step is to convert the field for the source in each subproblem into Cartesian coordinates. The third step is to rewrite the fields for the individual subproblems with respect to the observation point. And the fourth step is to compute the total field. So now let's consider the two specific types of problems that we dealt with. That is fields which were irrotational, followed by fields that were source-free. So we're looking here at computing the field for problems where the field is rotational, has a high degree of symmetry, and determining if superposition is required. We've already discussed the approach to take if superposition is required, so we're not going to basically deal with that in any detail subsequently. So in this case, basically, with a irrotational field and symmetry, we have a vector field equations, curl F equals 0 and divergence F equals rho. And the divergence theorem, we've mentioned before, we had a left-hand side involving a calculation over closed surface and a calculation over a volume. And so we basically are given what rho is, and so we can compute the right-hand side. And then because of symmetry, we're able to extract F, and from that we're able to determine what the field would be for a given geometry where symmetry applies. So the procedure for calculating F would be as follows. First of all, determine the nature of the symmetry, and then determine if superposition is required. If it's required, then we know we have to create a number of subproblems. Second is to establish the mathematical form of F and establish the shape of the Gaussian surface that satisfies one or more of the following criteria. The vector field F is parallel to ds, and F dot ds is constant on any of the discrete surfaces. Or the vector field is orthogonal to the surface area vector of any of the discrete surfaces. So we're looking for basically surfaces where one or the other of these properties basically is satisfied. So having done that, basically we have our Gaussian surface. Now we compute the left-hand side of the divergence theorem, and you only need to do it once. That's the nice thing about that. And again, just mention, if you memorize with the left-hand side, just mention how you would have gotten it in a very brief statement, and so that we understand that you know what the left-hand side actually represents. Fourth thing is to compute the right-hand side of the divergence theorem. and then you equate the left-hand side with the right-hand side, and then eventually you compute F. In other words, the vector field. Now, I basically put a table here which is more or less the same as the table that we showed in a previous lecture. I'm not going to go through it in any detail. The only thing of interest is to note here that for planar geometry, there are two surfaces which provide a non-zero contribution to the flux. So it turns out you have to do this in terms of two steps. First, you have to find the field external to the planar geometry, and because of symmetry, the field on one side and the field on the other side are the same, so you're only computing one value. Once you know the field on one side, then you can compute the field on the inside, because one surface field is known and the other surface is the one that you're trying to calculate, which is the surface interior to the object, particularly if you're dealing with a slab. All right, so that would be the procedure for a irrotational problem. What about where we have a source-free field? So in this case, basically, the only difference is that instead of applying the divergence theorem, we apply Stokes' theorem. And you'll notice here that the curl of the vector field is J, which is, if this electromagnetics problem, is a current flux density. The divergence is 0. And so on the left-hand side of Stokes' theorem, it's a contour integral around a closed contour. And on the right-hand side, basically, it's integrating over an open surface, which is bounded by the contour. And so effectively, the surface here can be chosen to be anything you want, but typically you want to pick the surface area vector to be parallel to the current flux density in order to make the right-hand side simple to calculate. So this part can be calculated, and here, because of symmetry, we can somehow extract the vector field, and as a result, we're able to compute F. So in brief, the calculation procedure to compute F is as follows. First of all, determine the nature of the symmetry and determine if superposition is required. Again, whether or not you need to create a number of subproblems. Secondly is to establish the form of F and establish the shape of the closed contour that satisfies one or more of the following criteria. One option is that the vector field F is parallel to the tangent vector on a contour segment, and the magnitude F is constant at each point on the contour segment. Hence, F dot TDS is either the magnitude FDS or minus the magnitude FDS, and therefore the magnitude F can come outside the integral. Or you're considering the fact that the vector field F equals 0 on a contour segment, hence F dot DDS equals 0. Or thirdly, that the vector field F is perpendicular to the tangent vector on a contour segment, hence F dot TDS equals 0. So you're looking basically for one of those three properties when you're basically designing a contour. Once you've established the contour, then basically it's time to invoke Stokes' theorem. So the first step is to compute the left-hand side of Stokes' theorem. And again, you only need to compute it once. The next is to compute the right-hand side of the Stokes' theorem. And of course, that's the part of the problem that's being given to you because you were given J. And the last thing is to equate the left-hand side with the right-hand side and therefore compute F. All right, so again, here's a summary of the different types of geometries that we considered. The planar case, again, is a special case, as is the case of the solenoidal, because we're dealing with a rectangular contour. And in the case of planar, you've got two unknowns on two sides of the contour. But as we did for the case of irrotational field, what you first try to do is to determine what the field is exterior to the slab. And because of symmetry, the field magnitude on one side of the slab and on the other side of the slab or sheet, whatever the case may be, is the same. So that means you're only solving for one field. When you go to solve for the interior to the slab, then you've already solved for the field exterior to the slab. And so now basically there's only one unknown, and that's the field on the interior of the slab. So in principle, it's a two-step process. In the case of a solenoid, basically can be done in one go. And so more or less, this is the approach that we've taken. And again, the left-hand side you can commit to memory, but just give a brief explanation as to how it came about. Okay, so let me then make some concluding remarks, given that this is the end of the course. I'll acknowledge the fact that this course has been intense, but you have a wealth of material to fall back on in future years if you want to dig more deeply into the subject. Look at the appendices and the reading assignments. Lots of information there. You'll find it very difficult to find that in other textbooks, and so you may find this very useful. Second is the course was difficult, but we needed to get you prepared for the course on electromagnetics, which is EC221S next term, which assumes that you have mastered vector calculus and in particular know how to apply the divergence theorem and Stokes theorem. All right, and then the thing which is probably more important at this point is the specifics of the final exam, which will be posted as a OneNote entitled exam. You will be told the content of each exam question and the marks assigned to each question. There are 6 questions. The exam posting will be uploaded after the last official day of classes, but no later than the weekend before your exam. We will be monitoring Piazza frequently in case you have any additional questions. And also for my own benefit, if you have any comments about the course and how to improve it, you can send me a personal email after your exams are over. Don't bother now, do it when you have some free time. I make changes to course every year based on the guidance I receive from students, particularly if it's constructive advice. This is the very first year that I have a complete set of notes and videos, and also the very first time we have test run the inverted classroom model. I would not be able to show you visuals and interactive figures in a traditional classroom setting. So I think there's a greater degree of richness in basically doing it this way around. The only thing is you have to be prepared in knowing exactly the questions that you need to ask me during the Q&A sessions. And finally, I wish you good luck on the exams and good luck and good health in the new year. Thanks very much. That's the end of the course.